This experiment is the Jobs method, or it's called the complex ion composition in solution. It means the metal to ligand ratio, and it's actually relies on the continuous variation of concentrations in solution. That's why the real name of the experiment is method of continuous variation, and Jobs is the name of the scientist who first started the method. For example, if we have a benzene and iodine in solution, the adduct formed is 1 to 1, and you have an intense color in solution by the 1 to 1 iodine to adduct. The same thing, we can look at the transition metal complexes in solution. Uh, some complexes we cannot isolate from solution. For example, nickel, when you put it with ammonia, you form 1 to 1 ammonia and 5 H2Os, 2 ammonias to nickel and 4 H2Os, 3 ammonia to nickel and 3 H2O. Now, these solutions cannot be isolated. The complexes cannot be isolated from solution, so we can characterize them inside the solution. And this chemistry is very important. It tells you how many ligands around the metal in solution without getting the complex out of solution. Now we have different methods. For example, you have spectroscopic method, UV visible, you have potentiometric titration, and all these methods depend on the equilibria in solution. Let's see next slide. The procedure to be used in determining the solution composition, which means solution composition means 1 to 1 metal to ligand, 2 to 1 ligand to metal, 3 to 1 ligand to metal. For example, in this experiment, we use ethylene diamine as a ligand, which is a bidentate ligand, and nickel 2 plus. Now we rely on UV visible spectroscopy and the colors to characterize our mixtures in solution. It's very important that Z is the nickel, for example, and NL is the N number of ligands, and ZLN is the complex throughout this experiment. Now, ethylene diamine, which is a bidentate ligand, binds nickel in 1 to 1, 2 to 1, and 3 to 1. Now, the ethylene diamine complex absorbs nicely in the visible, and the absorbance of the 1 to 1 is different, lambda max from the 2 to 1, different from the 3 to 1. And the absorbance of the nickel H2O solution is also different. So will depend on the absorbance from 400 nanometer to 700 nanometer to characterize our complexes. Now the ethylene diamine does not absorb in the visible, so we don't count the absorbance of ethylene diamine in this example. In this experiment, Z is a symbol used for nickel 2 plus, and L is the symbol used for the ligand ethylene diamine, and ZLN is the complex. Now we mix the nickel 2 plus and ethylene diamine to form Ni ethylene diamine N. N means 1 to 1, 2 to 1, 3 to 1, and the charge is 2 plus on the complex. Now we have different complexes with different intensities, with different lambda maxes in solution, depending on the ratio of the ligand to metal in solution. Now we mix the metal and the ligand, and this is the principle, and we take the absorbances in order to find the ratios according to the variation in the volumes. Which goes on steadily from 1 to 1 to 2 to 1 to 3 to 1 and so on. For because we have a bidentate ligand, so we form octahedral, so the maximum is 3 to 1. Now, we have nickel, aqueous nickel, plus ethylene diamine in the first equilibrium. So K1 forms a one-to-one complex with certain color, for example. This is the one-to-one complex, and the rest is H2Os. Now, the light blue color. Now, the first complex adds another ethylene diamine with second equilibrium with equilibrium constant K2, forms a darker color 2 to 1 complex ethylene diamine. Now the second complex forms a third complex with 3 to 1 and purple color, for example, with K3. Now, to see the complexes in solution, this is the drawback of the whole experiment. You have to have equilibrium constant K1, K2, K3 different from each other, so you can catch the complex in solution. And this is the limitation. It's a limitation of this experiment. So you have to have K1 greater than K2, greater than K3 in order to see these complexes in solution, the 1 to 1, 2 to 1, and the 3 to 1. Now, the major conditions in order for this experiment method of continuous variation to work, the equilibrium constants should be different from each other, so we can catch the complex in solution. So K1 must be greater than K2, and K2 must be greater than K3, so we can see the complex in solution. Now, the theory behind this experiment, as we said, we mix the Z, which is the metal, with N ligands to give the complex ZLN. So N determined by measuring the visible absorbance of a mixture of Z plus L, which forms a complex ZLN at equilibrium. So we have equilibrium, so we have metal, ligand, and complex in this equilibrium, and Z is the nickel in mole per liter, and we prepare this experiment 0.4 molar nickel sulfate in a volumetric flask 100 ml, and L is the ethylene diamine, M is the mole per liter, the same 0.4 molar. So we have equal concentrations of ligand and metal. You have to take care of this point. You prepare equal concentrations of ethylene diamine and nickel in 100 ml volumetric flasks, and all the volumes in this experiment are measured analytically, and the masses when you weigh and you prepare the solution. So if we mix X volume in mil or in liter from the ligand and 1 minus X volume of the metal, for example, to make the picture clearer, we have 1 mil ethylene diamine, we add to it 9 mil nickel solution, so we end up with 10 mil. To make the continuous variation, in a next sample tube we add 2 mil ethylene diamine and 8 mil nickel, so the total stays the same, 10 mil, and so on. Now, C1 is a symbol for the concentration of the metal, M is the molarity, 1 minus X is the volume, and C3 is the complex concentration. C2 is the ligand concentration. So in order to derive the equation which we are going to rely on, we have C1 equals M, the molarity, 1 minus X, which is the volume, minus C3, which is the complex concentration. C2, the ligand concentration, equals M times X, M the molarity, X the volume of the ligand, minus N times C3. N, which is the number of ligands taken, for C3 times C3. Now, C3 equals K, the equilibrium constant, C1, C2 to the power N. So at maximum, if we plot C3 versus X from this equation, the inversion point at the maximum, which is dC3 by dx equals 0, it happens at the inversion point, and so we plot C3 versus X, and the maximum gives us n equals x over 1 minus x. This is how we are going to take advantage of the absorbances we measure. We measure the absorbances and we plot, and at the maximum point we take n from the value of x. This is the theory behind the experiment. Now the absorbance equals the extinction coefficient times the concentration times the path length. Now the measured absorbance, always the whole mixture, E1 C1, eta 1 C1, C1, eta 2 C2 plus eta 3 C3 times L. Now the mixture of nickel and ethylene diamine, the absorbance originates from the concentration of the nickel and the concentration of the ethylene diamine and the concentration of the complex, the formed complex. So you have no absorbance for the ethylene diamine, you have absorbance for the nickel, so it has to be subtracted from the measured value. So Y, which is the subtraction of the background from the measured absorbance. So you subtract the absorbance of the nickel solution from the absorbance of the nickel ethylene diamine solution. It will be clearer later on. Now you have Y here, the absorbance in the form of Y, which is the absorbance of the mixture minus the absorbance of the nickel solution, versus X, which is the mole fraction. And the plot, you should use ruler, so you take the points going up and make a straight line, and the points going down you make a straight line. The maximum point here gives you X. Now nickel always corresponds to Z, and here Y is the measured Y equals the measured absorbance of the tubes, and you subtract the measured absorbance of the nickel, of course. This is the measured absorbance of the nickel. Now in the experimental part it will be clearer. This is the experimental procedure. I'll make it very simple. Now the first step, you prepare two solutions. First, 0.4 molar nickel sulfate in a 100 ml volumetric flask, as we said, always analytical in this experiment, use analytical equipment, and 0.4 molar ethylene diamine in 100 ml flask. Now what we are going to do to form different mixtures, that's why it's continuous variation, different volumes, then we take the absorbances at different wavelengths. Now in this experimental procedure, first you have to label 18 test tubes, clean test tubes. In the first 9 test tubes you label from 1 to 9. Tube 1 you add 1 mil ethylene diamine and 9 mil nickel, and the total will be 10 mil in the first tube, and you use a pipette to measure the volumes. Then in the second tube you increase the volume of ethylene diamine to 2 mil and the nickel 8 mil. So 2 plus 8 equals 10 mil, the total volume. So the mole fraction of ethylene diamine in the first tube is 1 over 10, which is 0.1. In the second, 2 over 10, which is 0.2. And the third, you add 3 mil ethylene diamine, 7 mil nickel. One after 4 mil, 6 mil, 5, 5, 6, 4, 7, 3, 8, 2, 9, 1, until you end with tube 9, which is 9 mil ethylene diamine, 1 mil nickel, and the total volume always is 10. Now, after you prepare these 10 9 test tubes with the mixture of ethylene diamine and nickel, you prepare the background tubes 1 prime to 9 prime. Instead of putting 1 mil ethylene diamine, you put 1 mil water, 2 mil water, 3 mil distilled water, 4 mil, and you add 9 mil nickel, 8 mil nickel, 7. So the background tubes 1 prime to 9 prime, they contain nickel plus water. So you have 9 mil nickel plus 1 mil water, 8 mil nickel, 2 mil water, and so on. And now you have 18 tubes to take the absorbance for at 530, 545 nanometer, 622, 640 nanometer, and you measure the absorbances of these tubes you prepared. And it gives you also the values. Now, how to handle the data. So you have recorded the absorbance 1 to 9 tubes and 1 prime to 9 prime tubes at 530, 545, 578, 622, and 640 nanometers. Now you have absorbance 1 for the 1 to 9. I called it 1 in red, A1. And you have A2, which is the absorbance of the background from 1 prime to 9 prime. Now it's simple. Why is the absorbance at any wavelength? For example, let's take 530 nanometer, absorbance A1 minus A2, which is the background, it gives you the first point. Now the second point for tube 2, which is the mole fraction here is 1 over 10, which is 0.1. The second tube, 2 over 10, the mole fraction is 0.2, and you take the absorbance at 530. Now you record 9 values and you plot Y, which is this value A1 minus A2, versus X, which is the mole fraction 0.1, 0.2, 0.3, 0.4, 0.5, until you get to 0.9. And the plot will give you points going up and points going down. With the ruler, you take all the points going up, straight line, and the points going down, straight line. The point of intersection gives you X. Now X is the mole fraction at which the maximum complex occurs at 530 nanometer. For example, assume x equals 0.5, so n equals 0.5 divided by 1 minus 0.5, which is 1. So for example, here you have a 1-to-1 complex, 1-to-1 complex. Then you repeat. Now you repeat all the plots at all wavelengths, y versus x, at 545 nanometer, 578, 622, and 640 nanometers. You get the ligand to metal ratios at all these. You get the ligand to metal ratios at all these wavelengths, and your report should include all the points at the written at the end of the experiment, the plots, 1, 2, 3, 4, 5 plots, and the ratios of metal to ligand at each plot, and the drawing of the complex at each wavelength. And this will conclude the method of continuous variation.